Okay. So before I plunge into the slides part, I wanted to, some of you, notably David Kutasov, asked me a question after the last lecture about this 1 over square root of n I got from the bubble diagram. And I wanted to clarify that this is really because when I went through this argument where I was erasing colors one by one, and then I obtained some two-dimensional, basically two-color graphs. And those graphs are not necessarily orientable. It includes both orientable and unorientable graphs. And that's why you can get actually genus 1/2 in the convention where chi is written as 2 minus 2g. And this is, so for example, if you look at this two-color matrix model that I discussed, the ON cross ON matrix model, I showed this figure 8 graph, and this clearly has 1, 2, 3 index loops, and this just contributes at leading order, right? But then there is this more tricky connection which includes the twists and the propagators. So I drew it explicitly here, and this tricky connection gives you, if you look at it, it gives you a term suppressed just by 1 over n, not 1 over n squared. So this corresponds to a graph drawn on RP2 rather than the two-sphere. And this is a generic feature of these graphs. So you can even get suppression by 1 over root n in principle. And we saw it quite explicitly because one of these g's can be 1/2 and the other two can be 0. But in some models, it so happens that these things cancel, it appears. But if you just take the generic d equals 0 scalar model, then you will get this very weak suppression of the large n limit. Okay, so I highly recommend for students to play with this combinatorics of both matrix and tensor models and basically go between the two. Okay, so since I have to conclude my lecture series today, and there is a lot of material to cover, I thought I will use the slides, and I will recap some of the stuff in the slides that I already told you. So for example, this, what appears to be the minimal Majorana tensor quantum mechanical model without randomness, is when you take these fermions psi ABC, and each index ranges from 1 to n, and then you have this Majorana anti-commutation relation here, and the Hamiltonian can be written like this with a shift, which makes it symmetric around 0. And I'll show some pictures of the actual energy spectrum. Okay, so the SON symmetry charges. So this model really has a full ON cross ON cross ON symmetry, and this includes the SON cross SON cross SON, and also some discrete symmetries which actually come in the precise spectrum determination. And these are the three symmetry charges that I already wrote down. So now so the coupling, as I mentioned already last time, I'm not sure if this works or not. Yeah, this seems to be, well, I'll just point with my finger. So if you think about the pattern of contraction between these psi's, you get the tetrahedron, which I already stressed, and the connection of this vertex picture with the tetrahedron. Yeah, thank you. Oh, great. Have to be careful with this one. Okay, so if you just shrink these vertices here and basically push these lines out, you get literally this one with the blue middle lines crossing under each other, right? And the propagator just is a triple line thing. Okay, so just to stress again, in this particular model, which has only one psi ABC field, the tetrahedral term is the unique dynamical quartic interaction. And quartic interactions, the reason I always go over this model. There are also more complicated models with more colors and more ONs, but then it just gets out of hand to draw the stranded diagrams. This one is sort of right on the verge of what is fun to do. And in this particular model, the other quartic terms which are connected are just the Casimirs of the 3 gauge groups, and they're colored like this, right? So these so-called pillow graphs are characterized by the fact that there are actually double connections between some of the vertices, unlike in the tetrahedron. And one color. So if you cut, for example, the red color, it just clearly falls apart into a product of 2 charges of the first type, and this is the product of 2 charges of second, and this is a product of third type charges. So the advantage actually, as stressed in the original paper by Witten on a somewhat different model, is that you can gauge these SONs, and then in that model, these Casimir operators will be identically 0. So you're basically restricting to the SON cube singlet sector, and then you remove the large degeneracies.
Can you construct higher than quadratic Casimirs?
Yeah, presumably, right. Yeah, in principle, even in this model, you could fine-tune the Hamiltonian to be higher order in size. Instead of psi to the 4, and I will discuss this a bit later. It so happens that psi to the 6, you can't write any term. They all vanish in the gauged model. But you can play with psi to the 8, for example, Hamiltonian, which is, I'm doing it now with graduate students. But the quadratic term is inherently a C number in this model, right? Because it's just psi ABC, right? And this is just because each psi squared is 1/2, so it's just a C number. Yeah, the other term I omitted nominally there is another quartic term, which is just psi ABC times itself, but that's just a C number. So that's another very nice thing, that there is no quadratic operator you can write down consistent with ON symmetry. The leading one is quartic, and there is a unique quartic one. In the context of SYK model, Chenke Xu in particular discussed a kind of different deformation, but that's not possible in this model. This is basically there is a unique dynamical quartic term. If you took a complex model, then things get already a bit more complicated, I think. Then. Okay, so what about the gauged model? Well, the gauged model is you basically add these, right? So one interesting question is how many...
Unique for the quantum mechanical case. If you go to field theory, it will not be unique anymore.
Well, in field theory, there is a Lorentz index, right? There is a Majorana doublet.
Gamma mu, 1, gamma 5, gamma 5.
That's right. Well, as we discussed several times. Yeah, once you go to fermionic high-dimensional models, of course, there is some proliferation of invariants. If you take a scalar theory, then it basically, as usual, is pretty dimension independent. But in the scalar theory, these pillows are not trivial, right? Because that's the difference. If you, for example, try to write scalar quantum mechanics with phi ABCs, then these pillow operators are dynamical. Okay, so one thing that we did in this paper was to count how many singlet operators there are. And for that, it's sufficient to just look at the free theory, right? The number of singlet, all that the Hamiltonian does is it mixes singlet states together. But if you just want their number, you can gauge the free theory and then compute the integrate out size, and then you get this nice integral formula for for count of the singlet states, just integral of some measure factor and a bunch of these characters like 2 cosine lambda a over 2. And these integrals can be done as a function of n pretty explicitly for low n. And you get the following result. So first of all, if n is odd, then there are no singlet states due to the famous anomaly, which I think is derived by people in this room. That if you basically, what happens is that suppose n is odd, then as far as each SON gauge group, there is an odd number of fundamental flavors. And such a theory is well known to have a quantum mechanical anomaly. Right. So this is basically why this model cares very much about whether n is even or odd. Like if you took a complex model, then there will be singlets for each one, but here it's you really need to take n to be even. And then when you look at n equal 2 model, that one just has abelian symmetry, and it's very, very easily solvable just by paper and pencil. And you find that the only singlet states are the ground state of energy E, which is something like minus AG, and the opposite state of energy plus AG. And then there are also 14 zero energy states, which are non-singlet. Then n equal 4 actually took a lot of work to do. If you just try to type it into Mathematica by brute force, it will crash. I mean, it's just too many integrals to do, but you can just expand it in e to the I and isolate the right term. So once you're clever, you basically see that there are 36 singlet states. And for a while, we were panicked because we received an email from someone saying, I think there are no singlet states above 2, so we really worked on it for a couple of days and got these numbers. Not all emails you receive are correct. Okay, but then for n equals 6, that's this 595 million. So there is this very rapid jump. And actually, the number of singlet states for large n, as I mentioned, there is this leading term, and at large n, the subtraction is only n squared log n. So in each sector, you will get a huge number of states, basically. There are various group sectors, representations, and you get a very large number of states in each one. And we're particularly interested in the singlet one, because the ground state, I can't say that I proved it, but here it did turn out to be this way, and it's very likely that there are various arguments that the ground state is a singlet. So you want to be in the sector with the ground state. And then the large low temperature entropy suggests that there are tiny gaps even near the ground state, according to the arguments that Subir presented. Okay, so now suppose you want to solve it for finite n. Since the word qubit already came up in Zora's talk, I just wanted to show you how we, for example, attacked the n equal 4 problem. And this follows the work of Krishnan and collaborators so you basically, so these psi's are just like Euclidean Clifford algebra, right? So it's like Euclidean gamma matrices in n-cube dimensional space. And there we know that when you construct representations, you always take some complex combinations. So you form these operators C, A, B, K, where the first two indices just range from 1 to 2, and the K index ranges from 1 to, or from 0 to 1/2 n minus 1. Right, so there are these ladder operators C, A, B, K, and C bar A, B, K, which just satisfy these relations. And then there is the ladder operator vacuum, which basically is annihilated by all C's. And then there is a conjugate vacuum, which is annihilated by all C bars. And then essentially for each of these operators you can associate a qubit, right, because there is a doubly degenerate state. And the Hamiltonian couples, so this A and B indices range over n values, so there are, while the last group is broken by this construction from On to Un over 2. And then you get like some sets of n squared qubits that are coupled together. So you get this type of quartic Hamiltonian. And this is the kind of thing you see in condensed matter papers a lot, right? It's a bit like some kind of non-local version of the Hubbard model, except there is no C bar C type hopping term. It's some kind of limit maybe of the Hubbard model. I'm not sure how physically interesting it is from the Hubbard perspective, but it's certainly the kind of thing you see a lot, and probably there are millions of papers with this type of thing. In it, the new feature is that the coupling, you see there are these, since all different A, B type sites are coupled together, you basically get a lot of non-locality. So if you think of, for example, A and B as some two-dimensional lattice sites, you get a non-local description. And I think Chen-Kek Su and collaborators are thinking about this picture where you think of A and B as actual spatial lattice sites, and C's as fermions that live on them. And then, for example, if K is just ranges from 0 to 1, that's sort of one variant of the model. That could be thought of as just a spin label. So it starts looking more like Hubbard type model. So now the Cartan generators of this UN over 2 are just these C bar. These are the individual U1 charges, right? And for the oscillator vacuum, each of these charges is minus n squared over 2. This is just the the usual thing that if you define charge properly in a manner consistent with charge conjugation invariance, you get these charges. And the gauge singlets clearly appear only in the sector where each of these charges vanishes. So each set of these n squared qubits must be at half filling. Like you essentially get the simplest state, the unique state at charge minus n squared over 2. Then you have to act on it with n squared over 2 raising operators. C bar raises charge by 1 unit. And that's where you get the most states, right in the middle. That's what we call half filling. So it's a rather weak constraint, but still it cuts down on the number of states you have to consider in this picture. So for n equal 4, you have a pretty simple situation relatively, because there are only 2 sets of 16 qubits, and they're coupled together by this kind of Hamiltonian. So there is just coupling within its sector, and then there is the coupling of the 2 of them together. And you have to take each of these 16 qubits just at half filling. And this cuts down the states a lot, because the total number of states is 2 to the 32, which is over 4 billion. But if you just look at having a half-filled sector in the first 16 qubits and half-filled in the second one, you just get 165 million. And this is actually well within what experts on Lanza's diagonalization can handle. In fact, I think the state of the art is already approaching billions of states. But this turned out to be not just amenable to exact diagonalization, but even remarkably enough, we could guess the analytic formula. And I'll show you what the analytic formula for all energy levels is. Unfortunately, it doesn't look like we'll wait for the quantum computer to handle this. I keep seeing these on my news feed, like the best qubits ever have been created or something. So there is seems to be like continuous progress. It doesn't look feasible, at least for exact diagonalization, but maybe one can do some kind of approximate diagonalization. So more about the spectrum of this gauged n=4 model. So this is the paper where we studied this 16 plus 16 qubits. And the trick towards isolating these states is very simple. We simply add to the Hamiltonian, actual Hamiltonian, something like 100 times the sum of the 3 Casimir operators. That obviously is going to make all the non-singlet states quite high in energy. And then if you have a Lanzas algorithm which only picks out, say, the first 40 states, you will see all the states you're interested in here. And there are various tests of this procedure. For example, you have to see numerically the e to minus e symmetry, and that showed up with very high precision. And we really have to thank Kirill for actually implementing all of this. So now, somewhat more theoretical question is, what are the remaining discrete symmetries? Basically, within each ON, there is a Z2 parity transformation, which acts like, by just say, flipping sign of all psi 1 BC. Okay? And then, as I mentioned, there is E to H to minus H symmetry, where you interchange 2 of the ON groups. But then, that means that there is a Z3 cyclic symmetry which preserves, which is actually a symmetry of the spectrum. Namely, if you just cyclically permute the indices, if you send the psi ABC to psi CAB, that's an element of Z3 which actually preserves the symmetry. And we know that Z3 group has 2-dimensional representations. So we will in particular see some 2-fold degeneracies. And then there are also 3-fold degeneracies when 3 of these parities are different. So you can ask, what is the full discrete group? And it turns out to be A4 times Z2, where A4 is the alternating group. So it has, I think 24 elements. Yeah. Okay, so it has 24 elements. I won't discuss this in detail, but this Z2 actually is just the product of 3 parities. The states separate into P1, P2, P3 being plus or minus. Okay, and here is the spectrum, just a numerical spectrum. You see, you can get quite a number of significant digits. The way this Lanzas works is that you repeatedly act with the Hamiltonian, and you see that for each E state, energy E, there is energy minus E. So the lowest state is singlet, and it also has all parity plus. And then you see, like, for example, the next state has this triplet, and it has parities 1, 1, minus 1, and their cyclic permutations. And then somewhere further down, you get another parity, all positive parity state. And then, so for example, it turns out that all energies can be expressed in terms of square roots. This is maybe somewhat special to this case. Essentially the reason all of them are square roots or nested square roots is because there are extremely few states with these quantum numbers. So if you, for example, look at states with parity 1, 1, 1, there are only 4 such states. So you know that the Hamiltonian in that block, the eigenvalue equation, will have the structure like e to the 4 plus 2a1 e squared plus a2 is equal to 0. That's basically restricted by the e to minus e symmetry and the fact that only it has to be a 4th order equation because only 4 states mix. And with that idea in mind, we made an ansatz for what it should be, and the numerics is very precise, so you can really determine these numbers here, and then there is a similar thing here. So at the very least, it's an amusing case where you can fish out exact eigenvalues from basically billions of eigenstates. Like, and
would you dare, for example, make bands and try to estimate entropies and see dependence of various quantities on entropies? Or this doesn't allow you to?
Well, so far we have rather few states, but yeah, we're actually working on some more like chaos, trying to see if that. I should say that while the ground state energy is this exact number, as I mentioned last time, the ground state wave function looks very complicated, and we haven't been able to make any sort of simple guess for it. In this qubit, maybe I should say what I mean by the qubit basis, right? Like you basically have a sequence of zeros and ones, right? Like, so you have like 0, 1, 0, that's the first 16 qubits. And then like say 1, 1, 0, that's the second 16 qubits, right? These are our states, and half-filled means that among these exactly 8 will be 1s and 8 will be 0s, and also among these 8 will be 1s and 8 will be 0s. But among these, that's 165 million possibilities or more. And the ground state just numerically has appreciable weight among millions among these states. So it's not some kind of simple thing that initially we were trying to guess, maybe something simple. So it's a pretty dynamical Hamiltonian, which looks very complicated. And also, as a disclaimer, I think this simple analytic structure will probably cease to exist for n equals 6, because there already there will be many, many states with these given quantum numbers. That's the expectation. So the polynomial will not be quartic. It's kind of a little accident that this happened here. Right. So let me just show you the energy distribution. What you often see here is there is some number of exactly zero energy states. Actually, an amusing thing is that here it's exactly 8, and these the symmetry group for zero energy states is somewhat enhanced, and it turns out to be the full cube group. It's a group of all the symmetries of the cube, including inversions, and these states can be thought of as vertices of the cube. So the 8 number, these are like coordinates of the vertices of the cube. You see all the parities as special significance states. Well, at zero energy, they will probably come all in these 8s. Like the number of zero energy state will be, this is sort of a simple representation of the full cube group. Yeah, in this business, for these models, you always get some exact zero energy states, and that's where the most states actually are. You don't see any parametrically large degeneracy, right? You only see these degeneracies like 2 and 3. Yeah. 3, I already exhibited why 2 appears and why 3 appears. But the ground state is degeneracy 1, and then there are some other with degeneracy 1. So there is an energy bound, so like at the next step there should be 600 million states with tightly packed into this region. In principle, you could choose to gauge some of even the discrete symmetry and only focus, for example, on states which are singlets under the discrete group. And that will like restrict you to only the sector of the ground state. So I think there is some space here for a good mathematical physicist to work on this Hamiltonian. Maybe one can prove some things that so far we've been able to prove some bounds which appear to be quite good, but for example, maybe one can directly prove how the gap in between the first 2 state scales for large n or something like that. Yeah. What? Horizontal axis is the energy eigenvalue. Yeah. These are we're plotting, so the energy is ranging from minus 160 to 160 in units of G. Yeah, this is determined from an energy bound. we have some energy bound that E naught scales as smaller than n cubed times g n 3/2. This is basically the right scaling in this large n limit. You have to scale g as 1 over n to the 3/2, and what remains is n cubed. But here we're working in units of g, so this is like n cubed times n 3/2. Yeah, we have some exact formula that gives this one. It turns out that for this n equal 4, the specific energy we get, 160, is very close to the bound that we could derive analytically from some kind of Cauchy inequality. I think the bound was something like 163, so it wasn't a bad bound. Okay, but the upshot of the story is that unlike in this, maybe I should show, since I mentioned this and now I'm free to show slides, I wanted to show the SYK distribution. Yeah, this is for a single sample of J's for NSYK equal to 32. Okay, from Maldacena Stanford paper. Probably Douglas will talk about such things, but here, as Subir said, you get a very smooth-looking distribution already just... so for numerical work, this model is extremely well suited. And you see like approximate E to minus E symmetry, but it's not exact. If you actually print out the energy levels, none of them are symmetric, and there's actually no strictly E equals 0 state. Like you see these little bumps here and stuff like that. Yeah, so if you sort of go to larger n or average the samples, I think it will get closer to the symmetric one. But here, for this model, the advantage is that even for small n, you get all these exact symmetries, and even including exact discrete symmetries. But the price you pay is that it's not so easy just even on a state-of-the-art cluster to get accumulation of states numerically. But maybe it's just a sign that we should work some more or be more creative about approximating. Because this is really the exact, what you would call the exact diagonalization. Like the numerically, all energy levels are known to many significant digits, and then using this logic, we even obtained this analytic formula. Okay, so now moving back to infinite n. Well, there, in some sense, so I already explained this part. This is exactly the same scaling solution as obtained for Majorana SYK model. You get this power law behavior, and the propagator is exactly symmetric under, anti-symmetric under interchange of coordinates. On some level, this was already done before, or very precisely, it's the same Schwinger-Dyson equation. Now, if you look at 4-point function, and you look at, for example, two fermions at different times, but with fully contracted indices, and then two other fermions with fully contracted indices, and you have to focus on the non-trivial piece, like there is sort of a leading trivial piece. We just contract these two together. But then the next piece can be done also via this ladder graph summation. So the crucial thing is that you have these, so in terms of dressed propagators, you basically have this structure. And you basically have a recursion formula relating different rungs of the ladders. It's a technique that was already applied before, I think first by Kitaev, and then by Maldacena, Stanford, Gross-Rosenhaus to solve this ladder kernel. And the kernel here relating n plus 1 ladder rungs to n ladder rungs is just given in terms of the 2-point function that you already determined. So you just basically need to do some integrals to determine the eigenfunctions of this kernel. And so here we didn't really have to do any original calculation, luckily. Another way to think about this, as in Gross-Rosenhaus paper, is to express the equation, basically use conformal invariance to think about the 3-point function of a composite operator. So the composite operators that we're looking at here are, did I write this down? Yeah, they all have the form, basically, they're just conformal operators that are schematically psi ABC dt to the 2n plus 1 psi ABC. And it's very similar to what was going on in the SYK model. There you just summed over all indices too. And then you essentially, in the scaling limit, you can use conformal invariance to fix this 3-point function in terms of the we already know what is the scaling dimension of psi, and there is some unknown scaling dimension of h, of this composite operator h. So this 3-point function is fixed like this. Then you just have to integrate this 3-point function with one letter rung, and the two should be equal. So this is the conformal Schwinger-Dyson equation. And then when you do this integral, you get some function of h. And of course, at the end, this factor here has to equal to 1. So the solution is just solving some transcendental equation, g of h is equal to 1. And the g of h comes out from doing the integral of k with this multiplied by this function. So I trust that Douglas will probably go over it in more detail because they worked it all out. But these are known as semantic integrals, or these are all doable integrals in terms of the basically gamma functions. So for this basic Majorana SYK model, you have only one g of h, and this turns out to be minus 3/2 times tangent divided by h minus 1/2. This formula has by now appeared in hundreds of papers, has been rederived in different ways. So then you just have to numerically solve this equation, g of h is equal to 1. And the first solution is analytic. You can just plug in h equal to here, and you see that then you get exactly, because then this 3/2 will cancel, and the tangent will give you, minus tangent will give you 1. So you have this first special solution, h equal to, and then there are some numerical solutions, 3.77, 5.68. And this h equal to is basically, that's the mode that's related to the Schwarzian, and it's related to Joukiffe-Teitelbaum dilaton gravity. It's essentially dual to the dilaton. And here, the higher scaling dimensions. It may seem a little bit mysterious why it's h equal to 2. Because this h equal 2 mode corresponds to exactly n equals 0. It's the very first operator. And this one you can just use the equation of motion to just write this as just psi to the 4. Namely, it's the Hamiltonian itself. And the first confusion you might have is the Hamiltonian itself, of course, h dot is equal to 0, right? So it's very hard to see how this operator at long distances can fall off as 1 over t to the 4. So there is a very long story in, for example, Maldacena Stanford. This really has to do with the fact that the theory is not exactly conformal. This particular mode is not exactly conformal. The 3-point functions of other modes are conformal, but this h equal 2 is not, and that's why people call it a nearly conformal model. So there is some big subtlety here. I'm not the best person to discuss this subtlety. I think Douglas will probably discuss it. Okay, but so as I said, this whole discussion is literally copied from earlier papers on SYK model. So what is new in the tensor model?
Igor, is there an argument that the 1 over n expansion coincides in different models, or it's just
Yeah, the 1 over n expansion is totally not coincides. In fact, the powers, that's part of the reason why I was even saying here.
So these are like two completions on string theory, or what?
Yeah, it's hard to know at the moment, but I'll just show you what I know about. So just the definite fact is that in this in the tensor model, there are definitely, in this model, there are corrections which are 1 over n, while in SYK model, in this language, they would be 1 over n cubed, right? So here, there will be corrections like 1 over n SYK to the power 1/3. That's the leading correction. And there is just, doesn't look like there is room for such a correction in the SYK model. And there is another big difference, which is the spectrum of operators. So in this, this model is like a quiver kind of quantum mechanics. In some sense, it's a very familiar looking model, right? The rules are completely clear, what you would call the invariant operator. So you basically just start connecting these psi fields, and each index contraction is different color, and just try to, for example, construct these connected graphs. And of course, some operator, and these, the ones that are connected is when the sum cannot be broken up into separate pieces. There are also like what you would call double sum or triple sum operators. Right, so for quartic operators, we already settled the question. There is this tetrahedron and 3 pillows. And there is also some generating functionals that compute numbers of these operators that you can. You could say that I also have a double sum operator, which is psi ABC squared, but that one just happens to be trivial. Now, if you look at 6 particle operators in this model, it's just the fact that all of them vanish by Fermi statistics. Just if you look carefully at how the indices are contracted, they all vanish. In the scalar model, of course, they won't, but in the fermionic. In fact, at the end of the talk, I will discuss the scalar model with this structure of interaction. But then you cannot do it in this Majorana model. So, but once you go to the 8th order, and then you restrict to bubble-free ones. Namely, suppose you gauge the model so you cannot, any insertion of such a bubble will zero the operator. So then, just by inspection, you can draw the 17 different colored diagrams, right? And they're all of the type psi to the 8. And you can ask, so what does it have to do with these operators? It turns out that one combination of them is related to this operator. Because if you use the equation of motion repeatedly, so here the equation of motion looks like this. Basically, you can use that psi ABC dot is G times psi cubed with same indices ABC. And this has some obvious internal contraction. So every time you differentiate, you can replace it by 3 fields without derivatives. This allows you to completely remove all time derivatives from operators and just write them without derivatives. Then it turns out that the sum of these 3 operators in the first column is this SYK-like operator, which is this one. So this we write as, for example, if you label them O1, O2, O3, so O1 plus O2 plus O3 is exactly equal to this this operator, which is psi dt cubed psi, up to a total derivative. But then there are 16 others. So you already see that there is more stuff. And in principle, you can start. I think the task of computing their scaling dimensions is very much in its infancy, because you have to work harder to write down Schwinger-Dyson equations for them.
But they're all supposedly irrelevant.
Right. Yeah, I think they're irrelevant, but still they're dual to some kind of other massive states they're part of the spectrum. For example, if you want to determine the complete bulk dual of the theory, you cannot ignore these operators, I would say.
Do you know how the number runs through?
Yeah, I'm about to show this on the second slide. There is, on the next slide, there is an interesting story that some of these operators have just additive dimensions. Like some of them you can show that the ladder corrections are suppressed by 1/n or something like that. And then there is a class of such operators. This we showed in our paper. But then so there is some interesting structure in their dimensions which we don't fully understand yet. Now, if you look, for example, at psi dt to the 5 psi, that one will be a 12-particle operator. Not a 10-particle one will be. It goes in 4. So there are 24 10-particle operators. These are completely non-SYK-like. They don't even occur at the same level.
So you say that there is a factorial growth?
Yeah, that's very clear.
But then you don't get but then the model doesn't even exist at zero temperature.
Right. I mean, that's basically the interesting thing about this model. Well, I mean, the Hagedorn temperature goes down as 1/log n. So log doesn't grow very fast. So, for example, if you assume that n equals 6 model with its 600 million singlet states is... Yeah, the infinite n model is, it's right on the verge of... Well, it's... usually, these type of models are suspicious in higher dimensions, right? But in d equals 0, where everything sits at one point, they don't really disintegrate physically, right? They don't become... Mm-hmm.
Doesn't it stick that there is a tachyon at the same time? Like even at zero temperature?
Well, yeah, maybe at low temperature something strange is going to happen. Yeah, but that's...
For that you really need a low temperature mode. This one is really
Maybe I'm confused. I mean, the model itself is completely UV finite and well defined by any n. So what's the instability here?
I guess the partition function may already at very low temperature of order 1/log n should become complex or something. But I'm not sure. I mean, usually what happens is, like in string theory, once you go beyond Hagedorn, we just say that the strings falls apart into bits, right? Yeah, so here maybe also, like somehow the theory may regulate itself and just go to... I think the crucial feature here, if you go back to this, for example, the formula for the number of singlets. Let me just show this again. Yeah, this formula here. Right, you see that this is the effect of gauging of the model. You see it's basically a subleading effect. So you can say that gauging is a small correction to the ungauged model. And at the same time, the fact that the model sort of sits all at one spatial point may help in defining it even beyond the Hagedorn temperature.
No, the Hagedorn temperature is on the thermal surface.
Right. Yeah, but it's right. It just shows you that something, like there is some kind of transition in the structure of the theory, right? But maybe the high temperature phase is well defined too. Don't know. Yeah, I mean, maybe thinking in terms of these gauge invariant operators just becomes bad at finite temperature, and you have to really think in terms of individual size. Right. Yeah, it's the model is not very confined. Yeah. Mm-hmm. Yeah, I mean, but but this factorial growth is certainly a very pronounced effect in this model, and it's various ways to confirm it. At least it's hard to fully prove it in the dynamical theory, but in the free theory, it's just a computation of some index, and you can see this k factorial 2 to the k pretty explicitly. But then this is part of the interest in these tensor models. Maybe they teach us about something. They're clearly not stringy. They're beyond stringy. And people who did quantum membranes also worried a lot that membranes are unstable for falling apart. So maybe they're sort of membrane-like. Yeah, one other sign, it may be partly numerology, that n cube in the partition function is similar to the n cube you see for the 5 brane, for example. The number of degrees of freedom on the 5 brane goes like n cubed, and that's beyond like the usual gauge theory. But this is a very crucial question about the fate of these models. Do they are they just curiosities, or maybe they teach us about some new type of gauge gravity duality? There's certainly always this gravitational mode, this h equal 2 mode, and but it comes with this huge baggage, these additional massive modes. Okay, so this I already, just for completeness to mention that there is this complex version of the model with un cross on cross un symmetry, and that has basically these types of 2 particle operators, and now n can be both even and odd. And in particular, the lowest one is this charge, just the U1 charge, which Subir mentioned in the SYK model. And this charge is protected, so it corresponds. Yeah.
Can you remind us why it's un plus ON, not UN cube?
Yeah, because if you look at the middle index here, there is no way to contract. You see that B1, B1 is contracted between 2 psis.
Always?
Yeah, you cannot make like if you insist that A and C are contracted between psi and psi bar, you're forced to contract B1 between two fields of the same charge. And that's why the middle index transforms under ON. In fact, if you read a lot of older literature on tensor models, they often assume UN cube symmetry. That completely removes this tetrahedral operator, which I argued is very, very crucial. Yeah, so if you want a tetrahedral interaction, you really are forced into this symmetry. And this is also true for the scalar model. So now there are basically 2 sets of modes. There are these, so the antisymmetric operators are exactly the same as in the real SYK model, same 2, 3.77. And then there is a new set of symmetric modes with 1, 2.65, and so on. And as Subir told us, there is a lot of interesting physics related to this charged mode, which is still being studied numerically, and it modifies the effective action, for example, modifies the Schwarzian effective action. But you see again that there is, so there is a possibility of turning on the chemical potential in particular. Okay, so now so far I've been like first in 0 and then in 1 dimension, and of course many people are curious whether there's any kind of quantum field theory where you can apply this exotic large n limit to. And the fact that there is a quartic interaction sort of immediately asks to be turned into a a 5-4 theory. So you can just write down a 5-4 theory with the kinetic term coupling each of these fields and this tetrahedral quartic interaction, just promoting the d equals 0 model I had to higher dimensions. You can say that this is just an example of 5-4 theory where you impose ON cube symmetry. And for example, one person who has been working a lot in such directions is Hugh Osborne. Like, he studies higher D theories with enhanced symmetry, so this just falls right in that direction. And then, so here, because it's again the same Schwinger-Dyson equation for the two-point function, apparently a similar equation was written down in 1963 already in an attempt to solve three-dimensional Ising model by Potoshinsky and Pokrovsky, and they pretty quickly discovered it doesn't give the right scaling exponent, but they certainly didn't know about this large N theory, but just wrote down this equation. So the solution to this equation is again like very similar. You get like 1 over p squared to the d over 4. As I already repeated a few times, this potential is not stable. Nevertheless, since at large N we're used to unstable potential, we can just still formally use it. And then you formally get this equation. And then the next step is, of course, to determine the two-particle spin-zero operators. Right? In this case, the spin-zero operators will have the structure phi ABC, box to the power n phi ABC. Right? You always need some box, like double derivative. Then there are also some operators with spin, but we can just focus on spin-zero. And there is a sequence of these operators. The first one will just be n equals 0 is just phi squared. It's just the anomalous, you're then adding the mass to the field. Right? Then the Schwinger-Dyson equation is, assumes this form, where the kernel is again just a product of two-point functions, and you get the equation to solve in this case. And when we started solving this equation, we for a while were somewhat confused, because if you notice, at large N, there is always the approach some asymptotic formula where dimensions go as N. But when we started counting backwards, we were missing a mode. And then we realized that this mode has gone to complex plane, like its H went to complex plane. So basically, the very first solution of this equation is complex. And it has the form d over 2 plus I times alpha. And study of such complex, I always thought that this is a catastrophic thing, but somehow lately it's become a fashionable thing to talk about such things. Like, for example, they appear in these fishnet models, and so I'll say a few more words about this. So how can we get some understanding why this mode appears? Well, we can go to 4 minus epsilon dimension, for example, where suppose you are still a bit in disbelief about your combinatorics and melonic truncation and all that, and you just want to do what we were taught to do, namely study 5-4 theory in 4 dimensions with these interactions. Then you essentially have a problem with 3 different coupling constants. If you impose also some discrete symmetry, you have the basic tetrahedron operator, OT. Then you have the sum of 3 pillow operators. Yeah, now they're perfectly respectable dynamical operators. And you have the double sum, like phi squared squared. So this is a renormalizable action. And you can just take the formula for 2-loop beta functions of 5-4 theory. There are tabulated formula. And you can use this formula. There's basically a formula for any interaction of the form phi I1, phi I2, phi I3, phi I4 times arbitrary tensor. And here the tensors are all given by products of delta functions. So you can actually read off read off the formula. And if you're curious about the complete beta functions, you can consult this paper in 2017 by John B. Tarnopolsky and me. In the appendix, there are full beta functions. And then we basically showed that, so then you can see from these full beta functions that you can scale them in such a way that the tetrahedral coupling goes like 1 over n to the 3 halves. The pillar one goes like 1 over n squared, and the double sum one goes like 1 over n cubed, and then the beta functions have a nice smooth limit. And they reduce to these rather simple expressions. Mind you, it's very important to go to 2 loops here, because the melons are inherently 2 loops. So the one loop is formally sent to 0 by the scaling. So you have to keep track of 2 loops.
I don't understand this entirely, because it seems like setting G2 and G3 to 0 is not self-consistent. In the end, you want to turn on only G1, but setting G2 and G3 to 0 is not self-consistent. Because of this 6G1 squared in the second line?
What happens is that, like if you say that this coupling is dominant, the tetrahedron one, then this equation is self-contained. But then this G1 acts like a source for G2 and G3.
So how can you discuss those 6 points where there is only G1, which is what
No, but that's the whole point. Yeah, I'm not. All I'm saying is that as long as they're scaled to 0 faster, this is exactly how this works. Like, so in the Schwinger-Dyson equation, I only kept this G1. But this story knows about G2 and G3, actually. Like, you're doing it a different way. This is somehow the really basic way of doing it through 4 minus epsilon expansion. And then you see that it really drags along G2 and G3, but with very suppressed and
the larger limit is not affected by G2.
right.
That's why it's active.
Yeah, but then what turns out to happen is that all the predictions from Schwinger-Dyson are correct.
Okay.
But this kind of explains why the complex dimension appears just on the language of 5-4 Feynman diagrams, because it turns out that while G1 is real, G2 and G3 are both complex. And this is just the dimension of phi ABC. You see that G2 star and G3 star do come in. And you get this plus or minus I square root epsilon also. And this is exactly what the solution is.
So the consistent scaling of this coupling is such that at large n, you can ignore G2 and G3.
Right.
For the
Schwinger-Dyson, right.
Even though you can ignore it, it gives you the right scaling direction.
But when the
They generated it by the Schwinger-Dyson diagram. So G2 and G3 explicit in their later diagram.
Yeah, there's somehow in there because for us it was satisfying to see that when you solve this equation and you say you plug in d is equal to 4 minus epsilon and solve this for h, you get exactly this answer. So somehow it's really included in the, right. They are really not like Schwinger-Dyson is not making a mistake, basically.
But again, you said that you are worried because there are these complex dimensions and now not. Why not?
No, I'm still worried. I'm just explaining why formally solving.
You say that something is.
Yeah. I mean, it's not a regular second order phase transition, right? But let's just. It's a kind of formal test of the consistency of the Schwinger-Dyson approach, and it also explains why. But it also shows you that because for example, if you're slightly below 4 dimensions, the complexity of these couplings means it's not like what you would normally call a CFT. Now there is this wave of activity on complex CFTs. It's precisely what you would call a complex CFT, like a solution where you allow some complex couplings. Okay, and then you can, for example, go to d equal 1, and then there is still an h equal 2 mode, but which is just the this phi box phi. So the 5-box phi operator still has h equal 2 from Schwinger-Dyson, namely the second solution. But the first solution is complex with a pretty large imaginary part. It's 1/2 plus I times a large number. So this certainly shows that it won't be like the usual. It's very far from being as good as fermionic model. The interesting thing is that when you see such a thing, this violates the, and you go to ADS-CFT, you see that the dual field in ADS-CFT is below the BF bound. Right? Maybe I should say again why this is, because the formula is that delta is equal to d over 2 plus or minus square root of d over 2 squared plus m squared. Right? So if m squared is below minus d over 2 squared, you get exactly the structure of dimension, right? You get d over 2 plus something imaginary, but the real part is d over 2. And that's exactly what we're seeing through the whole range in this model. That means that the dual ADS story is truly unstable because the tachyon is a bad tachyon. Right? This is this m squared BF, Brighton-Loner-Friedman solution.
Not even in the Klebanov-Witten
No,
window.
it's not. Yeah, that one would be like between minus d over 2 squared and that plus 1. But this is truly unstable, and that's why it picks up an imaginary part. I'll comment on this a little bit more, but I just want to show another. How much time I have? 25. Yeah. So let me just show another model where things work somewhat better, and so in this model. You still assume, for example, so this is one of the many variants of the model that you can consider. But now you take a phi to the 6 interaction, right? You take phi to the 6 interaction corresponding to one of these higher diagrams. This was a diagram that vanished in the fermionic case, but in the bosonic case, it's non-vanishing, and moreover, it's a complete square. So this is positive definite potential. This was one of the motivations to do this. One way to think about this model is actually comes from studying supersymmetry, because if you just take, for example, a supersymmetric model and write the superpotential W, which is, say, G times phi A1, B1, C1. So this is now a superfield phi A1, B2, C2, namely the same tetrahedral structure. B2, B1, C2, phi A2, B2, C1. So you take this model then, and you find that W prime squared is precisely this prism operator. In other words, it's the square of the derivative of this superpotential. So you just square this phi cube thing with 3 indices. So it's as if like you took a supersymmetric model and just crossed off the fermions, which is like, it's a way to complicate the model in some ways, but then one can see how far you can get. And actually for large n solution, it's convenient to introduce, so this was an auxiliary field contained in phi, but you can just bring it back and rewrite the action in this form. Okay, so now you have, so this also shows you why this prism model, in terms of this additional field, it's like still tetrahedral in some sense. So in terms of phi fields, the diagrams are somehow more complicated. So this looks like two glued tetrahedra together. And the gluing is accomplished by this quadratic term. But then when you, so this is a somewhat different approach to Schwinger-Dyson, because you have two fields, and then you generate an induced term for chi, an induced kinetic term, and you want it to dominate at low momenta over this chi squared, which means that it should actually blow up as p goes to 0. And interestingly, there is indeed such a solution. In fact, an SYK-like model of this sort, first we weren't fully clear on it, but it was considered by Murugan, Stanford, and Witten in this very nice paper, which contains many things. And this is one of the sections, like 6.2 or something like. It's called Another Attempt at a Model. So this model is, you can also write like a disordered version of it, where you have J times some interaction coupling 3 phi's and a chi, and the chi squared type term. And they already derived Schwinger-Dyson equation for it, but they only focused on d equal 2 case, because they were looking for some new conformal behavior in d equal 2. And in d equal 2, they actually stumbled on the same type of complex mode that I showed in the. But we were primarily motivated by the same story that I showed you before, namely trying to do 3 minus epsilon expansion for this model. Because in 3 minus epsilon dimensions, it's weakly coupled. So you can try to look for a weakly coupled fixed point. We saw that in the 5-4 case, we kind of failed because already in 4 minus epsilon, there were some complex values. But so when you solve for the for the 2-point function, you find the following constraints: that 3 delta phi plus delta chi is d, and delta phi has to lie in this range, so that basically the solution is okay in the IR. Namely,
Here the larger limit is just the melonic diagrams again.
Yeah, they're melonic. In terms of phi's, they're more complicated. In terms of phi's and chi's, they're basically melonic. Yes. Right. And and you have you have this restriction because you really want this. As I mentioned, there is one new feature. Like, for example, the phi propagator in momentum space has to be small, like sigma has to be smaller than p squared. But chi propagator has to just have a negative power of p altogether. Like, so sigma chi has to scale like p to something negative. Only then do you have like a good infrared solution, and that's where these bounds come from. And then you get, so then so this is work with a group of collaborators. Did I mention it here? Yeah, Jambi, Popov, Prakash, and Tarnapovsky. And then once you derive, for example, the equation for delta, you see that it looks somehow much more dynamical than in the previous case. In the previous case, delta was just d over 4. So there were no higher epsilon corrections. And that looks very strange, right? Because in an honest field theory, usually you pick up like some series in epsilon and stuff like that. And here you see something much more like what you expect, that even the leading this solution exhibits the whole series in epsilon and so on. And in particular for 2.9, you can also solve it numerically, and it's not too far from this series. Okay, then what about bilinear operators? So there are different types of bilinear operators. Yes. Okay. Yeah, I think. So the bilinear operators come in two types. What we call type A. Type A is of the form phi box phi plus some A chi box chi. Okay, and then there is type B, which will be like phi box chi, some kind of mixed operator. And these really mix together, so you have some interesting structure appearing here. And then you find actually that as you push the dimension down, this complexity comes to hit you again. So you see, for example, that for 2.9 dimensions, the lowest dimension, which is phi squared, it basically sits here, right? It sits here. This is the right root to correspond to the operator phi squared. Then this curve starts to drift up, and the two solutions kind of merge. And when they merge, it's exactly d over 2. And here the real solution is missing. So you again get two complex conjugate solutions. And you can just verify that this is what happens. And this is like a scenario of merger and complexification of fixed points that we see in many, many physical systems. So what happens is, for example, nevertheless, slightly below 3 dimensions, the dimension of phi squared has a perfectly sensible epsilon expansion. But then some kind of branch point develops as a function of epsilon, and then it becomes complex. The interesting thing is that it stays complex in this range, including 2, and this is completely in agreement with Murugan et al. But then around 1, it goes away.
Sorry, Igor?
Yeah.
For d equals 2, so I was trying to think of this complexity as coming from the fact in the previous case that potential was unbounded from below. But here it's not. So how can you get complex numbers? I mean, and d equals 2 is a totally kosher thing, right?
Yeah, I'm a little confused by this. It could be that if you...
Indicative of a first order transition.
Yeah, it's a first...
Yeah, it's a first order.
So it means you're somehow like you're not at the right saddle point or something?
It's always like this. When two eigenvalues merge,
Mhm.
become complex. It's indicative of the chiral symmetry breaking to confine a...
It doesn't mean that there is some...
Is there a correlation function that falls off with that power?
Oh, with complex thing?
Yeah.
No.
What is this?
Yeah, it means that there is some other phase of the theory that,
It's the first order.
That's what we usually say, like for... So it's not directly related to this non-perturbative instability that you see in phi. Oh, in phi 4 theory, you could say that there was never any second order transition. Here, you actually do see... And then, so...
In phi 4 theory, there just wasn't anything. I mean, the theory just runs off to infinity.
No, but
So
I think... No.
It's large n.
It's large n, so at large n, things that run off to infinity are sometimes okay.
Well, not really.
No, they are. I mean,
They're exponential.
yeah, no. But this is more of a, you really see a merger of fixed points here, and we verified it very explicitly by doing epsilon expansion, which I have to say in this case is a much more involved task because. No, we didn't. Well, in the large n limit, we just see that that this exact numerical thing happens. Yeah, we didn't do it via this epsilon. You see that the epsilon expansion for this operator is badly behaved. That you see pretty.
This is in the larger limit or for any n?
This is in the large n limit. That's the beauty of it. That the Schringer-Dyson allows you to determine the large n limit. But you don't know the 1 over n correction. Yeah.
Supposing you do that for small epsilon.
Right, exactly. In fact, we did this. So
Why does it happen exactly d over 2? In many cases like that, where two eigenvalues merge and you get the first order transition, the real part is not d over 2.
somehow here it's always d over 2. I don't fully... Maybe because secretly, because there is this chi-squared structure. It's always d over 2 if you have a double trace interaction, for example, in matrix model. The ones I encounter are somehow usually d over 2. And then you can say that this is really dual to this Bryden-Lange-Friedman instability, I think. But granted, certainly at small n, it's not d over 2. And yeah, so this is the... yeah, I did not, so maybe So this is the story of complex fixed points. They basically may appear after two real fixed points have merged, and they usually correspond to weakly first-order transitions. I mean, it's a very simple story that if you have, for example, a beta function that looks like this, right, then the theory will flow to here. Then you change a parameter, and then it looks like this. Then you just have some slowdown of the RG flow, so you see the walking behavior near here. And when this point is very nearly touching, you can hover near here for a long time, and this may explain some puzzles about some, like on a lattice, it can be very, very hard to distinguish between first order, weakly first order and truly second order phase transitions. Like
transitions here from where to where?
Transitions from where to where? Well, usually they're
Like at the map.
right.
With the Goldman phase and the
Mhm.
So this would be some
Yeah, symmetry broken, exactly. Yeah, in fact, you see that the operator that picks up complex dimension is also somehow the operator that dictates the phase structure of the theory. Yeah, the leading relevant operator. Suppose you look when you're still in the real phase, right? Then there is an honest second order phase transition similar to continuous symmetry breaking.
There are lots of options. You go in cube, where does it go down to?
Well, just if I develops a VEV, for example. Yeah, but you definitely can add this m squared phi ABC squared. And classically, when you change the sign of m squared, right, you have to tune this operator first, right? Well, usually if you develop phi, you break all the ON symmetry. Like it's you maybe. Yeah, maybe there is a diagonal. Right. Yeah. Mhm. Yeah, you say that then it goes to single ON. Or, but basically, there is the classical picture and then the quantum corrections. But it seems like it generically happens that when this leading operator that causes the breaking of symmetry, when its dimension formally becomes complex, that's when you no longer have a second order phase transition. Okay, this I already said. Okay, so let me just show you what you need to do in 4 minus epsilon dimensions. If you go back to this picture, you actually have to include these things, right? Because to keep the theory renormalizable, you have basically this prism one, then this one we call wheel interaction, and then you have to also add these with maybe in some particular combinations. And these are just single sum. Then you have the double trace ones and the triple trace one. So you really have a system of 8 possible coupling constants.
But the fact that you got this complex dimension doesn't, it means that theory is not unitary.
I would say it's worse than non-unitary. Yeah.
At least not
Yeah.
unitary.
No. Yeah, people often use the words non-unitary. I would distinguish between, to me, non-unitary means that there are real scaling dimensions, but you're below unitarity bound. That's often okay, right? Like the Yang-Lee point or all these 2D CFTs with negative C, the minimal models. to me, those are realizable, right? You can see them on a lattice as second-order phase transitions. These, I think, you can never see as second-order phase transitions. You can at best see them as some slow crossover or something like that. But let me just show you that. So this I didn't include. It's pretty technical, but you can again, if you look at our paper, you can basically reproduce these expressions by honestly taking. For example, you can reproduce these epsilon expansions by finding the fixed point for all 8 couplings. So we have this system of couplings G1 up to G8. And again, you can complain like, oh, you're admixing the non-melonic terms. But again, the solution is that only this one is dominant. So you scale G1 as G1 tilde over n cubed, but already G2 you scale as G2 tilde over n to the 4, and so on. So all the other ones are more suppressed. Okay, and then you find an honest real fixed point, no longer complex, honest real fixed point, and at this fixed point you actually reproduce then the large n limit of this sequence of fixed points reproduces this large n epsilon expansion. And moreover, you see that, first of all, this also allows you to compute 1 over n correction. Like, for example, you can see plus 1 over n times some couple of epsilon terms. So it's the first sort of 1 over n correction calculation. Not done through Schwinger-Dyson, but just through this standard perturbation theory. But moreover, you also see that, for example, as you vary n, there is some merger of fixed point there too. So even this 3 minus epsilon fixed point, as you vary n, collides with another fixed point for n around 54. And then they become complex. So you can have a lot of fun with these collisions of fixed points in this theory.
What was the dimension of phi as a function of epsilon?
Oh,
Had it on the formula?
right, right. Yeah, this one does not go complex, I think, by itself. At least not in this leading order. But the thing about phi squared is already at leading order. It becomes complex. So to me, there are many interesting questions left. One is, what is the fate of this theory in D equal 1? Because formally it does not appear to have any complexity problems there. So could this give some kind of, so D equal 1, is this a reasonable nearly conformal model? It again has this H equal 2 mode and all that. So that may be worth sort of a more careful look. And I had also like some brief discussion that similar complexity phenomena can also occur in fermionic models in D equal 1, but maybe I should, since I've said so much already, I'll stop and ask for questions.
About this K factorial, is there some claim that this large n, if you pick some energy, the number of states below that energy grows like E factorial? Or, but you were talking about numbers of operators.
Right.
The actual spectral.
No. Yeah, I thought you expect the density of states in energy space to be. Again, this is not something I studied rigorously at all, but the expectation is that it's similar to SYK model, and it just grows as a power,
So
like near the
what are you
edge.
talking about, factorial growth? Because the thing that's relevant for all this stuff people were talking about is
Well, the question is, how do you see the
energy.
right? Yeah, there is just a picture of states and low energy dynamics. Yeah, I don't know where in there is buried this problem with factorials.
In there meaning the
Yeah,
energies.
right.
But it's not like you're saying that the entropy goes with E log E. That this is not a claim that's being made.
At least my expectation was that you just have some kind of, like in SYK model, rho of V goes like, so I think the expectation is that rho goes like E minus E naught square root, right? That's what you see in SYK model. We certainly have not seen this numerically in our model because it's just so hard to make the spectrum dense. But that's, yeah, so near the edge I would not expect to see anything particularly anomalous, right? Like, well, the spectrum has a bounded range. You always get some kind of curve like this, like with a lot in the middle and then it falls off, so it's by definition it's going to vanish as some power here. Yeah, I don't know what, maybe there are some features of the spectrum as you go a little higher in energy, but if you just, I think this operator picture, maybe it's not so important for studying, for example, the chaos in the low energy model. But if you try to construct a dual of this model in near ADS2, right, then I thought you were supposed to, for each gauge invariant observable, put in a massive field. It could be that there is some complicated dynamics involving these massive fields. Like one thing that I can imagine happening is that these fields are made of like a lot fewer more fundamental constituents. And these more fundamental constituents are the ones that really play a role in the bulk. So you're not supposed, maybe we should not be afraid of this K factorial because there is some compositeness in these operators. And we see some hint of that because the dimensions of them seem to be like additive in some more fundamental blocks. But this is really something I don't know the answer to. No. I'm not talking about this model. Yeah.
Any other questions?
I was referring to these funny let me just say it because I think it's a useful thing to, like basically if you look at some of these operators, for example here, you can ask what is its large unscaling dimension. It turns out that when you write down the ladder corrections, they're all such that they're suppressed by 1 over n. So the large n dimension of these operators is 8, the number of fields times 1/4, and the complexity of diagrams only comes in at higher order. So that's what I meant. That they're for a bunch of them, and others are like sums of 2 particle energies, or there is some, but definitely a whole bunch of them is just the number of fields times the exact dimension of one field.
SYK, most of them have the larger end.
Yeah, but here it's exact.
Here it's exact.
Yeah, here.
Still,
Right.
most of them
Mm-hmm. Yeah, asymptotically, the corrections become pretty small. Right.
Yeah, just to try to maybe another interpretation of the phase transition that you found, that becomes first order, that if exactly d over 2, the double trace operator becomes relevant. And therefore this is exactly what we did with the Solia 10 years ago.
Yeah, no, that was certainly what I had in mind. For this 5 to the 6, there is no obvious double trace.
No, I mean just 5 squared. So at exactly that point, the double trace operator.
And
that would be exactly like the tachyon in the string theory that you found.
Right.
So that would be, I mean, so you do also expect decoupling in n equals 4 with this double trace, maybe complex dimensions for the same reason.
Yeah, I think that's true. There are certainly also these for example, this phi chi operator, that's a phi to the 4, so you have to worry about that too. Yeah, so you're saying that there is an additional relevant direction that appears when.
Exactly.
Yeah.
And that infinity, which is the first part.
Yeah, that's exactly the merger of fixed points that you see a marginal rate.
If there are no more questions, let's thank Igor for all of his set of lectures.
Improper spacetime. Could you see the random matrix behavior from the improper spectrum, like
Well-
the level spacing distribution?